Now we see another CNN named VGGNet. This is the general architecture of a tiny VGGNet. There are only 15 different layers in this network, with a pooling layer after 2 consecutive convolutional layers. As for AlexNet, the end of the network is composed of fully connected layers. The receptive fields in the convolutional layers are of size 3 by 3, which is the smallest size capable of capturing the notions of top-down, left-right. The stride is set to 1 and the padding is used to preserve the spatial resolution after convolutions. Pooling layers with 2 by 2 receptive fields and a stride of 2 are used. All activation functions are ReLU. Note that the local response normalization does not improve the performance. Indeed, nowadays, this type of layers is not often used. The most important idea in VGGNet is to use small receptive fields by noticing that a receptive field of size 7 by 7 can be obtained via 3 consecutive convolutional layers of size 3 by 3. Note that one 7 by 7 convolutional layer applied on an image, depth 1, has 49 parameters, whereas 3 by 3 convolutional layers have a total number of 27 parameters. Therefore, decomposing convolutional layer into a sequence of convolutional layers with smaller filters reduces the number of parameters. This can make the whole network easier to train, but also reduces the expressiveness of the network, i.e. its ability to model any type of relation between the inputs and the output. All in all, it has less parameters, is easier to train, but less flexible. Here are different variants of VGGNet, each one in a different column. The architecture must be read from top input layer to bottom output layer. Only the number of layers and the number of filters differ, but all filters are of size 3 by 3 or 1 by 1. For example, Conv364 means that a 3 by 3 convolutional layer is used and produces 64 feature maps, which correspond to 64 different filters of size 3 by 3. Remember that the ReLU function is used after each convolutional layer and that the end of the network is composed of fully connected layers. The depth of the network increases from the left to the right. Regarding the optimization procedure, the weights are initialized via Gaussian distributions and biases are all set to 0. This holds for network A. For the others, the weights from network A were used as the initial values and the others were initial via Gaussian distributions. Stochastic gradient descent with momentum is used. The batch size is set to 128 and the learning rate is the same for all layers and follows this heuristic. The training phase lasts 74 epochs and the L2 penalty is used together with dropout. Results are presented here. The test set error is of 6.8, whereas that of AlexNet was of 16.4. This is a major improvement. However, VGGNet is expensive to evaluate and uses a lot more memory. Indeed, it has around 140 million parameters. The large number of parameters mostly comes from the fully connected layers. In general, in CNNs, fully connected layers need a lot more parameters than convolutional layers. It was since found that these fully connected layers can be removed with no performance downgrade. This reduces significantly the number of necessary parameters in the network.